Alright guys, so this is me doing the 2016 final exam. Sorry for the video being uploaded kind of late. I didn't have time to do the entire test before, but it should be up on Sunday, which is today for me. Okay, let's start this exam. We're going to start with the first question, which is, which of the following reaction sequences is likely to produce a cyclic product? Okay, well, if we do the first one, if we do this first question, I know the first part is Br2 water. Well, that adds a Br on the less substituted side and an OH on the more substituted side. And then the second part is NaOH with water, which is for us more specifically NaH, which is just taking your OH minus and taking that H off. If you take that H off, well, that's gonna make a O minus, which directly attacks the bromine spot, and then you do form an epoxide, which is a cyclic product. So W is one of the answers. Let's look at the next one. NBS was find the allylic spot and put a bromine on it. So the first part will be to make this thing. Then is to do BH3, THF, H2O2, NaOH, and water. So if you do that part, well, that's hydroboration, which adds a H and a OH with OH going less substituted side. But notice that I have NaOH here, so the NaOH is actually I believe taking the H off again, so just like we did before, and in this case you get the O minus, which is going to again attack here, and the bromine leaves. So this time we end up making a 1 2 3 4. We make a 4-atom ring like that. So that's one of those weird ones. X also makes it then. Then we look at Y. Y is going to make Br2, so we go make 2 Brs. And then you have NaOH. Well, at this point, NaOH can't do anything. If anything, it's going to just do either elimination or substitution. Let's say if it was doing substitution, well, it will just substitute that spot. So nothing else is happening after this point. Y would not be an answer. It's not making a cyclic product. And then we look at the last one, which is HBrROR. Well, that one makes a H and a Br, with Br going less substituted side. And now you have NaOH again, which is going to take this H off like that, form the negative, and then the negative attacks the Br spot. So this again makes a cyclic product. So it can't be all of them. It's Y, X, and Z, which is B. Next question, what is the major product of the reaction shown below? Okay, according to the chart, this is the top left quadrant. This is strong nucleophile, strong base. Strong nucleophile, strong base on a secondary actually goes for elimination. So it should be an E2 reaction. And we know that E2 should be an anti-elimination. So this is my bromine that's on a secondary spot. Again, we know it's E2 reaction. So I need to take an H off from the beta spot. This is the alpha spot, this is the beta spot, and this is the beta spot. This reaction is supposed to be Zeit-Steph. So if you look at this beta spot, this one is secondary, while this one is tertiary. So we have to take the H off of the tertiary spot. Currently, the H is actually cis to the leaving group. So you can see that both of these are wedged. So that's currently not allowed because this reaction is supposed to be an anti-elimination. So all we have to do is we have to flip this side around where the H actually ends up going dashed. So I'm going to flip this side where it goes like this. So if I redraw this, let's keep the left side the same. We'll make this bromine, we'll make this H. And then we're going to make the H go to the ethyl, ethyl go to the methyl spot, and the methyl goes to the H spot. So we'll end up getting dashed H. On the line will be the ethyl, and wedge will be the methyl. Now my bromine and my leaving group bromine and the H are trans to each other, which is how this reaction works. This is how the reaction worked. So now you can totally do the elimination where your OCH3 picks up this H, and then this goes here to form the double bond, and then the bromine leaves. So all I know is this ethyl and this ethyl have to be trans to each other at the end. So there, in this answer, they're not trans. Here you went anti-Zeit-Steph. Here you're in the wrong spot. So it's between C and D. And again, we figured out, well, it can't even be C because this one doesn't have an ethyl. So it would have to be D. If I redraw exactly what this is, I have a ethyl, the double bond goes here, you have an H here, you have the ethyl on top, and you have the methyl on bottom, which is D. So the answer should be D. Alright, going on to number 3. Number 3 is, which of the reactions generate a meso compound? Alright, let's go from the beginning. The first part is H2PT. Well, that makes, that adds two H's to each other. So let's say that both of the H's came in as, let's say, wedged. Well, then both of my methyls will be dashed here like this. If the methyls are dashed, then we do R and S. So if I do it for this spot, I would get, let's see, 1, 2, 3. This one would be R. I get R here. And this one would be 1, 2, 3. This one is S. So yes, I have two apparently chiral centers that have the same substituents, one being R, the other one being S. This is a meso compound. So this one works. Let's do 2. 2 is, we're adding Br2C Cl4. Well, that makes anti Br and Br like that. If we do R and S here, I get 1, 2, 3 S for this one, and I get 1, 2, 3 R for this one because we flip. Same thing. We have two allegedly chiral centers that have the same substituents, but one is R, the other one is S. This is again a meso compound. So 2 is also one of the answers. If we do OSO4, now I would get 2 cis OHs like this. And then we do R and S again, so I get 1, 2, 3. This one is S. This one is 1, 2, 3. This one is R. Again, same thing. Two alleged chiral centers that should have the same substituents. One is R, one is S. This is also meso, so it's also 3. And then we look at the last one, which is MCPBA and NaOH H2O. So the first part is MCPBA, which is gonna make a cis epoxide. So let's say that the epoxide went in as a wedged. So let's say we had a wedged epoxide like this. So if you made the epoxide like that, you would have you would have the dashed methyls there. These methyls would be dashed. And at this point, you're doing NaOH, which can attack on either spots. So let's say the NaOH attacks like here. It doesn't really matter. It has to be an anti-addition. So if you're going to attack here, it's going to come in as a dash. So the dash is going to be my OH, and this methyl is going to end up being wedged. This methyl will stay wedged. And I mean, this OH will stay wedged, and then you'll get that. Just remember, this is how you make trans diols. In the end, I'm getting this as the answer. So let's work out the RNS here. Well, I got 1, 2, 3. This is S. I got S on this side. The other side, I'm getting 1, 2, 3. This one's S, but it's actually R because you gotta flip it. And again, we have the same thing. Two alleged chiral centers with same substituents. One is R, one is S. This is again a meso compound. So it's actually all of them. Cool. Next question. Okay, the number of isomers that have the formula C5H8Cl and F and a 5-membered ring is, okay, since I have a 5-membered ring, you can't have a membered ring with chlorine in the middle because this won't be neutral anymore. So the maximum amount of ring we can have is 5 atoms, and they're all my carbon atoms. Okay, moving on. If I try to place my Cl and the F somewhere, well, one way I can place them is I can place them on the same thing. So this is one answer. Notice this is not a chiral center, so there is no wedged and dash answer here. Another answer would be if I place this and this, so they're at 1 and 2 positions. Notice this side has 2 chiral centers. So if you use the formula 2 to the n, well, I have 2 chiral centers, so there's 4 total stereoisomers possible for that one. And then I do another one. So now I'm going to place them 1 and 3 to each other. Well, again, it has 2 chiral centers, so if I follow the formula 2 to the n, I would get 2 to the 2 again, which it gives me 4. So there's 4 possible options for this too, and those options would be like wedged, wedge, dash, dash, this one being wedged and this one being dashed, and then the other way around, this one being dashed, this one being wedged. Those are my 4 options. And then I can't move it over anymore. Like if I try to go 1 and 4, I guess, well, that's just 1 and 3 from this side, so that part doesn't matter. So these are the maximum amounts. You have 1 here, 4 here, 4 here, so a total of 9, which is B. Okay, cool. Next question. How many of the following compounds have a dipole moment of 0? I'm going to erase this. So I'm going to have to make the compounds again. You have a butane. You have a cis-2-butene. So that looks like this. You have a trans-2-butene. You have 2-butyne. You have cyclobutene. And then that's it. Okay. So, which one have a dipole moment of 0? Well, I know this has a dipole moment, so this can't be it. This has a dipole moment of 0. This has a dipole moment of 0, because both are the same pulling. And then this one doesn't, because there's a double bond here, so this one wouldn't be 0. But this one would be 0 because you're completely away. The way this pulls, the way this pulls, this pulls. So everything is tied up there. Okay, and your answer should be, I guess, 3 of them, so it's B. Next question. How many stereoisomers are formed in the reaction of the following compound with HBrCCl4? So if you do that reaction, you should add a H and a Br, so the Br, let's say, goes here. We know that once you add this H in the beginning, you can form a, like, okay, this is how you want to treat this question. I think it's easiest if you treat it like this. So if I'm going to add the H and the Br, you have to ask yourself, well, how many chiral centers did I make? The thing originally is not chiral, but in the ending, I make chiral centers, and those chiral centers are here and here. So there's 2 chiral centers, so you follow the same formula. You go 2 to the n equals, 2 to the 2 is 4, so there's 4 possible stereoisomers, which is A. Next question. The correct order of increasing acid strength, the weakest acid first of these is, okay, well, here I have a carboxylic acid, which is better than alcohols. So I know one of these has to be the best ones. Between the alcohols, the one that has the chlorine is going to pull more. So this one, Y, is better than W. So the weakest acid would be W. If weakest is W, you cut out C, D, and A. Next, I know should be Y. So both of these are W and Y. I can't decide right now. Now I have to pick between the carboxylic acids. This carboxylic acid doesn't have any chlorine, so that one would be the weakest. So I have next thing as V, which is for all of them. And between these two, the chlorine is closer here and the chlorine is 2 away here. So you can see this is the alpha spot, this is the beta spot. This is the alpha spot, this is the beta spot, this is the gamma spot. So in the X version of the answer, the chlorine is closer, which makes it better. So the answer has to be B. Oh no, I mean, we have to pick the best acid as last. So the answer needs to be E, actually, I'm sorry. So the weakest would be this, because no chlorine and alcohol. This one is next, chlorine with alcohol. This one is next, which is carboxylic. Then it's carboxylic with Cl, but Cl being far, and then carboxylic with Cl being close. The total number of unhybridized valence shell orbitals in this structure is, okay, well, I have this part as being sp3, this is sp, this is sp, this is sp, and this is sp. Okay, bunch of sp. Well, I don't have any h's, So it's just every sp is supposed to be 2 unhybridized. So I have total of 8, which is none of the answers, so the answer is none of the above. But you have total of 8 unhybridized. 2 for each one of the SPs. Next question is, the specific rotation of pure S is -30. Okay, so I know S turns in negative and R turns in positive. A sample containing both enantiomers is turning in the positive. So I have more, it's turning in positive, so I have more of R. And now we can do the formula. Enantiomeric axis equals absorbed over pure. Absorbed is 24 over pure is 30 times 100. You cancel this. 3 goes into 24 8 times, so I get 80. This is how much extra R we have. So 20 is going to get split evenly. You would have 10% S and then total of 10 plus 80, so 90% R. They wanted the amount of S, which is 10%, which is A. Alright, moving on from the multiple choice. The first question here is to draw the structures and name the isomers for C7H14. So just to begin, the first thing, that have at least one chiral carbon, and you can't have any rings. Okay, the first thing I do before an isomer question is to do the degrees of unsaturation, which is 2C plus 2 minus H minus any X's plus any nitrogens, all divided by 2. So I have 2 times 7 plus 2 minus 14, all divided by 2. 7 times 2 is 14, 15, 16. 16 minus 14 is 2. 2 over 2 is 1. So I get 1. Remember, 1 degrees of unsaturation could mean 1 double bond, or it could mean a cyclic. But they told us no rings, so I have to have 1 double bond on my thing. I know I can't make a 7 long chain like this, because if I make a 7 long chain, it won't have a chiral center, even if I put a double bond. So let's make a 7 long chain anyway, and then what we'll do is this. We'll go 1, 2, 3, 4. That's 5, 6, 7. So this is a double bond. So the way I would do it systematically is I would just erase the methyl and I would put it here. Well, that's not a chiral center yet. So let's move in another time. Okay, that is a chiral center. So that's one answer. Then again, I can copy this. Copy, paste. Let's keep the double bond at the end. We'll erase this methyl and we'll put it up more. So that's another answer. And at this point, I have nothing, so let's remove 2 carbons now. So we're going to copy this answer again, and then this time we're going to remove that, and we'll remove this, and we'll place this methyl here. Well, we have the chiral center there. Here the chiral center was there, here the chiral center is here. So that's another answer. Okay, another answer we can do is... Okay, so I think those are the maximum amount I can do. Oh no, I think we can also do this one. So you can also have methyl here. Let's say here, and then the other methyl can go here. This also works. Why not? This would be another answer. Okay, another answer we can do. Okay, so all the answers I've made up till right now, the double bond is like at the end. So let's move up the double bond once. Why not? So if I move up the double bond like this, then I can place the methyl, let's say right there. That's one answer. And then this one might have been tricky, but you can also have a cis double bond like that. So those are the ones I could come up with like that. Alright, all of those have the chiral center, none of them are rings, so awesome. If we do the naming, well, the first one is going to be 1, 2, 3, 4. So it should be a 4-methyl. This is hexene, so you can do 5-hexene, or you can do, 1 hexene, or you can do just hex-1-ene. So let's just write 1-hexene, like that. Next one, now I have 3-methyl, 1-hexene. Now I have 3,4-methyl, so 3, 4 dimethyl, 1 hexene. Then we have 2,3 dimethyl. One hexene. Oh, except it's not a hexene, it's a pentene. I think the one before was a pentene too. I'm sorry, this was a pentene. This was a hexene, okay. This one is 1, 2, 3, 4, 5, 6, 6 again. And then this one specifically, you have to start with trans first. And then I have a 1, 2, 3, 4 methyl. And then it's a 2 hexene. The next one's gonna be a cis. And then you go 1, 2, 3, 4 again. 4 methyl, 2 hexene. Just like that. Okay. Again, I don't know if you're gonna have one of these isomer questions. You didn't have them for the exam 1, so you might not, which is gonna be great then. But if you do, this is how you practice it. All right, next question. So when I sent out the email, I said, hey, you might not know how to do this question, which is fine. This is kind of like an overkill, I feel like. So if you totally want to just skip over this question, feel free to do that. If what we went over during the practice problem session was enough for you, boom, you got it. Just keep it that way. Don't mess with it. This is it. But if you do want to know how to do this question, it just adds a little bit extra, which is this resonance energy thing. So as we know, if we look at this molecule in the beginning, we know that those two double bonds are conjugated, so they have resonance. And having resonance is a good thing. So if I take this reaction right now and I put it through H2PT or whatever is happening here, well, my molecule is losing resonance, right? So in the beginning, my molecule had resonance. So there's two new things you have to know. You have to know, so we can either go from a molecule that was good to something that was bad, or a molecule that was bad to something that is good. Currently, for our question, our molecule in the beginning had resonance, which is a good thing, to it losing resonance, which is a bad thing. So we went from good to bad. So if you're ever going to go good to bad, that energy is treated as minus X. We're going to treat whatever that energy is, we're going to give it a minus X. If the, no, actually it's plus X, I'm sorry. And if the energy is going to go, if your molecule was already bad, so let's say your molecule had a bunch of strain, and then it went to a molecule that didn't have strain, well, that would be bad to good. So that one goes minus X. So again, to reiterate, for our question, our beginning thing does have resonance, which is good, to something that doesn't have resonance, which is bad. So our resonance energy will be plus X. But otherwise, let's say if I was going from this to this, right, then that's bad to good. So then you would want to use minus X. That's it. Okay. They're telling us the heat of hydrogenation of 1,3-butadiene to butane is negative 205 kilojoules per mole. So I know that's my delta H. And now we have to do the bonds broken to bonds broken minus bonds formed. So I know it's bonds broken minus bonds formed. So let's write out the different types of bonds I have in the reactants. Well, I have one C-C bond. I have two C double bond C's. I have 1, 2, 3, 4, 5, 6 CH. And I have 2 HH. Those are what I have in the beginning. Then at the end, I have 3 C single bond C. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 CH, and that's it. So if we look at what happened, well, we had 1 CC and then we went to 3 CC. So 2 CCs were formed. So we're going to write this on this side, 2 CC. We had 2 C double bond C and then we didn't have those. So we broke 2 C double bond C. We had 6 CH and then we had 10 CH, so we formed 4 CH. Then we had 2 HH, which we don't have anymore, so that goes 2 HH. So all of this minus all of this. Now, normally you guys learned this question just like this and you were done. So we just had that extra thing for, they want us to tell us what the resonance energy is. And again, I told you this thing in the beginning is good, and then we're losing that resonance, so we're going to bad. Good to bad, that resonance energy is going to be plus x. So plus x. We do the entire thing plus x. Okay, and we're trying to solve for x. All the numbers here, we're given all these numbers already. So if I erase this top thing here, let's write out all the numbers. Well, I would have negative 205 equals, in the bracket, 2 times C double bond C is 620 plus 2 times 440 minus 2 times 350 plus 4 times CH is 410. All that plus X. So I'm going to bring out my handy dandy phone now to figure out what this exact number will be. So let me use my phone. Give me a sec. Actually, we can maybe even do it here. Nah, I'll do it on my phone. So 2 times 620 plus 2 times 440. I get 2,120. So it's negative 205 equals 2,120 minus 2 times 350 plus 4 times 410. I get 2340. All that plus x. Wow, big numbers. 2120 minus 2340 equals negative 220. So I go negative 205 plus 220, and I get 15. So after doing all of this, if you solve for x, just normal algebra, you should get 15 kilojoules per mole. So this is a long question. Mainly I want you to be able to get this. If you can get that, I'm good to go. Again, you didn't have this plus x thing to worry about, so I don't know if it's really important for you guys. Alright, for the second question, it says the heat of hydrogenations for cyclobutene to cyclobutane is this, and the strain energy of cyclobutane is 800. They want us to know what the strain energy is for cyclobutene. Okay, let me think about this one. The strain energy of a cyclobutane is 100. Actually, I don't think you have learned how to do this question, so I'm gonna skip this question. You don't have to worry about this one. This one is actually too much. Both of the things have strain, so you shouldn't really have this question. Let's ignore that question. If you ended up doing it, my bad. Let's go to the next question. Okay, the next question is to make your Gauss butane chairs and stuff. So this one says, use the chair templates below to draw the structure of the most stable conformation of each of the indicated compounds. So we have to make the most stable every single time. Now, I know it's confusing because they're telling us to make the most stable conformation, but then they're like, oh, tell us which one is the least stable one. Okay, so this is what I was trying to explain in the email, but this is how we do it. First, we have to draw the most stable of cis and trans. You have to do that. So if I was to give you both of them, it would look like this. So this one, I have a methyl and a cl, and I know methyl is the big bad guy. So here, let's make the cis version of it, and here we'll make the trans version of it. Okay, so if I make the least stable, no, we have to make the most stable version of cis and trans. I'm sorry. So if we make the most stable version of cis and trans, well, if it was cis and 1 and 4, I would go 1, let's put it in the equatorial spot like that, and then they have to be cis to each other, so this one will be pointing up like that. If I'm doing trans and I'm trying to make the most stable again, I will put this on top like this, and the CO would be pointing down like that. Okay, so this is the most stable of cis 4-methyl cyclohexyl, and this is the most stable for trans 4-methyl cyclohexyl. Now the question is saying to pick out of these two, which one is the least stable stereoisomer? Is the cis one worse or the trans one worse? So out of these two, I know the one that's better is this one, because this one is not interacting with anything. There's 0 kilojoules per mole, but this one is the worst one. So again, what we did was we drew the best cis and the best trans, and then we're comparing the cis versus the trans to figure out which one is the less stable one out of the two. And for us, it happened to be the cis one, and that's the one you were supposed to draw. So I know the directions are really confusing. Again, for all of these, we have to draw the most stable conformation every single time. So next one, we're going to again draw the cis and the trans version of both. This looks horrible. Let me draw that again. So, okay, so we have to make the most stable for both of them. So call this cis, call this trans. Okay, so this is 3-methyl cyclohexyl chloride. So the methyl is again the big bad guy. So let's make the most stable. We'll call this 3, we'll call this 3. Here I have to make it cis. The methyl is pointing up on both of my things. So here it would be pointing up chlorine, and here it would be trans where it's pointing down. So out of these two, they want us to pick which one is the less stable one. Well, again, this is 1 and 3 to each other. There's no interaction. This is 0 kilojoules mole. While this one, the Cl interacts with the 2 carbons on the bottom, or these ones. So you interact with this, interacts with this one, and over here, there, if you count to 4s. So out of these two, the worst one is that one. So you were supposed to make this. Next one. Again, we're going to do the same thing again. We have to make the most stable both times. So we make the most stable of cis and trans again, cis and trans. I have 2-methyl cyclohexyl chloride. So if I want the most stable, let's put the methyl on equatorial spots like that. And then cis would be, this also points down like this. This one would be trans where it points up. So out of these two, they want us to pick the one that's the most stable. Well, the most stable one would be this. This one only has 1 interaction, while this one has 1 interaction here and then 2 with the chlorine on the bottom. So the more stable one would be the trans version. Next one, this one is 1-methyl cyclohexyl chloride. Since they're both on 1, there is no cis and trans here, so we can just make the most stable version of it. Well, the methyl would have to go equatorial, and then the chloride would go in axial. That's literally my only option here. So if I want to make the most stable, at least. The product of the reaction of BRF with cyclohexane. The product of a reaction of BRF with cyclohexane. That's a reaction you haven't learned, so we're going to ignore that. Sorry I didn't cancel that out before. Alright, next question. This is a structure of cocaine. Cool. Please answer the following questions about this molecule. How many sp3 hybridized atoms are there? Well, that's all the ones not involving double bonds and stuff. So I should have, let me count this first. 1, 5, 6, 7, 8, 9, 10. Okay. So I get the number as, so this is sp3. That's 1. This is sp3, 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 sp3. This one's sp3. This one's sp3. This is sp2. You have to know this has resonance, so this one's actually sp2 also. The oxygens are both sp2 because they have resonance. They can go this goes up. So those ones don't count. And this one is sp3. And I think that's it. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I get 10. Cool. sp2. Well, sp2s are gonna, let's do it in blue. I know this is sp2, 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 and literally all of these 1, 2, 3, 4, 5, 6. All those are sp2. So 6, 7, 8, 9, 10, 11, 12. You should get 12. Cool. Next, number of chiral carbon atoms. Well, let me erase all of this so it's not confusing looking. Alright, the chiral carbons are right there. One right there. One right there, and one right there. There should be a total of 4. Next one. Number of unhybridized atoms, not including the H's. Well, every single sp2 that I have will have one unhybridized. So if there's 12 sp2, there's going to be 12 unhybridized. Simple as that. Actually, let me think about this question for a second. Number of sp2 hybridized atoms. Number of unhybridized atoms. Like completely unhybridized? So the answer here should be 0. And the reason is because all the atoms are at least partly hybridized. When they ask for unhybridized atoms, I think what they... Like for us, what it should have said was number of unhybridized orbitals. Number of unhybridized orbitals would be 12. But then the atoms, there is no atom that's like completely unhybridized. That would only have to be H's. So this is like the old type of question they used to have. So I wouldn't worry about that too much as long as you can figure these out. Okay, let's move on. Next question, use the templates below to draw Newman projections of the most stable conformation of the indicated compound. Put the chiral or lower numbered chain chiral carbon in front. Okay, so 2-butanol would be like this. And we have to make it R, so this is 1, 2, 3. This is R right now, so I have to make that. We have to make the OH part in front, so we're going to draw this from 2 to 3 like that. So I should get this H, CH3 pointing down, CH3 pointing up, and these are H's, just like that. Cool. Next question. Did I get this? Yeah. Next question. Meso 2,3 butanediol. Okay. So that would just be like this, wedged OH and dashed OH. I think this makes a meso. So here you have a R, this is a S. So that's a meso compound. Well, here I would get OH on left. There would be a H on the back. This would be the OH, OA, H, CH3, and CH3. That's the best conformer. Again, we're keeping all the big stuff away from each other, which is perfect. Next one, 2S, 3S, 2-bromo, chlorobutane. So I have a butane. I have to make a 2-bromo and 3-chloro. So 2 has to be an S. Well, we have to make that dash then. Bromo, because this is 1, 2, 3. That's R, but it's S, yep. And then the second part on 3, you have to make that part a S also. So we make this a dashed chloro, because then it goes 1, 2, 3. This is R, but it's actually S. Okay, so you would make this, which just looks like Br, Cl, CH3, and then CH3, and these are H's. So you would get that. So as long as the stuff is next to the correct spots, you're good to go here. So like if these H's are together, or like just like that, you're good to go. Same thing here, if the H's are together and these are, you'll be correct. Yep. All right. Again, for all of these questions, you can see that the two big bad guys were as far apart as they can from each other. So we are making the best structures here. All right, next question. Draw dash line wedge projections of the following compounds starting from the template given. Okay, we kind of just did this, but okay. 2,3-dimethoxy butane. We know methoxy is OCH3. So if I got to make an R here, well, R here would go 1, 2, 3. That's going S. So I just have to make it dashed. O methyl. So you can see now I would get 1, 2, 3. This is looking like S, but it's actually R. The other spot is 3 has to be R. So R here would also need to be dashed. OCH3. So you can write ME or CH3. Let's write CH3. So I would get 1, 2, 3. This is S, but it's actually R. You flip it. So you would get that. Next one. 2R, 2-fluoro, 3-butane. So we just learned from the last one, if you want to make R here, you make it dashed. So this is F. And then 3 has to be S, so let's make that one wedged. And we'll make this the I. So it goes 1, 2, 3. This is S. Okay. Next one. S3-chlorocyclopentene. So since it's a pentene, we can make the double bond. This is 1, 2, 3. So I gotta make it S. So we'll make it wedged. Chloro. Now I get 1, 2, 3. This is S. So you have to make that part wedged. Just like that. Cool. Alright, next question. Draw the structures of the named compounds. Okay, so first one's a bicyclo. You have a 2, 1, and a pentane. So you have 2, 1, 0. So I know the middle part has to be like this. It's 1, so one part is like a cyclobutane, I think. The other part's like this. So I think something like this, because you cancel these out, and then this is 2, this is 1, and the middle is 0. So you would make something like that if I make it bigger. Something like that. Next one, trans 6-chloro-4-hexene 2-thiol. So total thing is a hexene on a 4. So 1, 2, 3, 4. Like that. 2-thiol. SH. It is, I did make it trans. 2, 3, 4, 5, 6. 6-chloro, like that. I think that's it. Cool. Next one. 1-propoxy 4-pentyne-2-ol. Okay, so let's make a pent 2-ine. So this is the triple bond. No, it's 4-pentyne. 1, 2, 3, 4. Okay, so total is pent, so we're gonna make it like this. Okay, so now I have 1, 2, 3, 4. So on 4 I have a pent, 2 is the all, so like this, and then 1 is a propoxy, which is oxygen, and then like 3 carbons, like that. Okay, super weird, super long, but there it is. Just like that. 1-cyclohexyl 4-fluoro 3-methylbutane. So main thing is a butane. On 3 I have a methyl. Call this 3, call this, or I'll go the normal route. This 1, this 3. On 3 I have a methyl, so there you go. On 4 I have a fluoro. There you go. On 1 I have a cyclohexyl. So this part is a cyclohexane. Like that. Super weird, okay. Bicyclo 2,2,1-heptadiene. So to get 2,2,1 I would get 2 here, 1 in the middle, and then 2 here. So it should look like this. This is 2, 2, 1. So you're pretty much just making a cyclohexane with the little thing in the middle, like that. Okay, next one. Give the IUPAC name for each of the following compounds. Well, here the longest chain is like these. Okay, and then between the ethoxy and the alcohol gets the lower of the number. So we're gonna go 1, 2, 3, 4, 5, 6, 7. So you should get 7 ethoxy, 3, what is this? Heptanol. Alright, next one, the double bond has to get the lowest possible number, so I would go 1, 2, 3, and I wouldn't go the other way around because then the substituents get the lowest number. So I should get 3 on this and 5 on this. So you go 5 bromo first because alphabet, then 3, 3 dichloro, cyclopentene. Now notice you don't have to say 1 because the double bond's always at 1 in a cyclic. Between a double bond and a triple bond, the double bond takes priority. So this has to get 1, 2, 3, 4, 5. So I have a 4-fluoro And then you can name this multiple ways, but I'm going to do it the way I like it here. So I go hex 5-ine 2-ene. I like it this way. You do it whichever way you like it. Alright, next question. A reaction of 2-methyl-2-butene. So let's make that first. So like that. With Br2 and methanol forms a bromoether in 3 steps. Using curved arrow show it. Okay, so we're starting off with this thing. And they want us to put this through Br2 and methanol. So the first part's to form the bridge. So this attacks it back, and this goes here. So I form this bridge with the positive plus Br minus. After this step, I have my methanol, which is CH3OH, that can attack the more substituted side. So it's going to attack over here, and Br is going to come off. So I make my Br, this OH, and CH3 with a plus. Okay, and then last step is to deprotonate. So you have your bromine. So another one of these. We'll take that H off from here. That step should be reversible, and my final answer is this. OCH3. There you go. That's just memorization and doing it over and over again. Alright, next question is to just do a what kind of reaction? This is just elimination. So let's do this elimination. You actually, okay, let me think. OH. So this is on a primary alcohol. Since this is on a primary alcohol, we learned primary OH for elimination does E2. So we're going to do it like that. So the first step should be to protonate. We're going to use our H2SO4 to protonate. You can also just say H+, or you can use HCO+. Let's use HCO+. So this goes here, and this grabs an H. Totally reversible. So I form OH2 with a plus. At this point, you can do your E2 elimination. So let's write it on another step. OH2. So we're going to have water pick up this H. This goes here, and this comes off all in one step. Just like this. So it used to be taught a little bit differently, but for us, I believe this is how we were taught. Although I expect on the test, if they give you this, it'll probably be a secondary alcohol. So look out for any rearrangement. That was on the last exam. So this plus H3O plus. No, plus water also, because it left. There you go. Next question. Write the major organic products of the following reactions showing stereochemistry as necessary. Okay, HBr, ROR. Well, that reaction we know is supposed to, there's no cis or trans for that one. That one's just a radical reaction, so you have to remember radical reactions can kind of make racemic answers. So let's say the Br went in as wedge like that. This part won't change. So the Br on this spot could have ended as a wedged or a dashed. So we get this answer plus this enantiomer. And then the thing is, originally my methyl could have came in as like a dashed. So this part again doesn't change, plus enantiomer. So it can go in either way. Doesn't really matter. Yeah, so this one is like, let's say this is the RS answer, so you would have the SR answer. This is the RR answer, so you would also have the SS answer, like that. Next one, NBS. These are the allylic spots, and the one that's the most substituted is the one that I just circled. So at that point, you have to remember you would do a little resonance, so this goes over here. Final BR should go over there. So if I make that out, I would get the double one in the middle, and then this BR can go in wedged or dashed, like this, plus it's an enantiomer. BR2H3 can add in the middle here. It goes to a tertiary spot, but since that's not a chiral center, there are no enantiomers. Cl2, remember, it's not super selective. In fact, in this case, I have 9 primary spots, so the major product wouldn't even be the tertiary. Instead, it would actually be over here. So you would only get that as the major answer, which is tricky. So you have to remember the little chlorination ratios there. Next question. Well, in this one, your bromine originally can come in, let's say, as a wedged. If it comes in as a wedged originally, then you would have a bromine here as wedged. And then the methyl would be wedged. This bromine. So here the bromine's added trans. Another answer would have been if they came the other way. So you can write plus enantiomer. If you want to see what that answer is, well, this bromine came as dashed. This one is wedged, which makes this dashed. That's why I wrote plus enantiomer. So this is it. Next one, write the true propagation steps for the reaction of 1-butene with NBS. So this one was just like this. It's 1-butene, so I started with that. So let's make our 1-butene. This is your H. You have the BR with the dot. So you go half goes here, half goes here, and then the last half goes here. So once I make that, I get the little dot here. You do your little resonance. The resonance makes it go in the middle because that's more stable. Plus your HBr. The second step is to use your molecule now, like this, with Br2. This goes here, and this forms the Br bond. So I end up getting the final answer, which is this, plus Br with the little dot. Those are your 2 propagation steps. Next one, they want the first propagation step or free radical chlorination of an alkane. Okay, well, if you have an alkane, let's say, like this one, you would have this H and a chlorine like this. So half goes here, half goes here, half goes here. You'd form the chlor plus HCl like this. Not so bad. Next one. More questions. Yay. Okay. Normal reactions. COCl2 DMSO NET3. This is Swern, which is a mild oxidizer. So my primary alcohol should turn into a aldehyde like this. CH2I2 ZnCu, that's a carbene reaction. So that makes a cyclopropane like that. HBr CH2Cl2. So we have to figure out what made that go to that. Well, notice that I still have a double bond, so that means originally I started with a triple bond like that. So this was one equivalent specifically. Okay, this one, you went from that Br to having an extra carbon there. Okay, the only way that's possible is first if I do NaCN with like DMF or something, and then you do H2PT. So the first step was to make a CN, and then we reduced it to that. Next one, NaCN, acetone. So this is a little tricky, please mind this. If you have NaCN here it's not going to attack the epoxy side. It's just going to do a SN2 instead. So the first step is to make this CN. And then now, since you already did your substitution SN2, now the NCH32 can attack on that spot. So my final answer should be OH here. This is your CN, and then this N methyl attack that side. This is a super difficult question, I feel like. If you didn't get that one, it's okay. Next one, PBr3. PBr3 turns OH into a BR, and then it's also doing inversion. So the methyl is dashed in the beginning, the OH will be turned into a dashed BR, and then you're doing SCH3. So this is gonna do another SN2. So your final answer will be a dash CH3 and a wedged SCH3, like that. So it's inversion then inversion again. All right, next one. H2SO4 CH3OH. This is again BLAM, but we're working with acid now, so we have to go the more substituted side. So the OCH3 has to go more substituted side. So if I make my cycle with this, more substituted side is there, so you have to come in as a dash. So look, you would get the OH here, and then the methyl will end up being a wedged, and the thing that comes in has to come in dash, which is my OCH3, just like that. Next one, Cl2 water. Well, that's gonna make a trans. Oh, this one's a little tricky. Oh, actually, it doesn't matter. Okay, look. So you're gonna add a Cl and a OH, and then the NaH is gonna take this H off. You get a negative, which attacks this, and this leaves. So it was a way to form the epoxides, like that. Next one, having excess HI. The first step was to make this. You get a positive, and then you have I minus, which can just attack one of the spots, and this leaves. But the thing is, you have to remember this overdoes the reaction, so you form the I here, and you form the I on the other one too. You keep doing it. And the reason for that was the other side is making an OH, but you still have more HI available. So you're going to protonate this. Once you protonate this, you'll make OH2 with a plus. And then this I minus is going to like attack again, and this leaves. That's how you make this answer. So you get both answers being I. Refer back to the notes to know how we did that. Next question is the thing with the CR. The thing with the CRs are strong oxidizers. So you would make a primary alcohol, go do carboxylic acid, like that. Next one is TSCl. You have to remember TSCl doesn't invert the stereochem. So the first part is the CH3 stays the same. This turns into OTS, stays wedged, and then you flip the stereochem. So the final answer is N3, like that. Next question is a little tricky. So look, I have total of 1, 2, 3, 4, 5 atoms here, and then I also have 1, 2, 3, 4, 5 atoms there. The triple bond is turning into an aldehyde, so I'm thinking SIA, the Cia reaction, but notice this alcohol turned into a carboxylic. Now there's a mini problem here that like when you do what reaction totally matters here. So if I do the BH3Cl first, well, then I'm going to end up making this thing. You'll have your OH here, and then you'll make your aldehyde. Now if I do a strong oxidizer, both of them are going to turn into carboxylic acid. I don't want that. Only one of them is carboxylic, the other one is aldehyde. So I have to do the H2Cr2O7 first. So let's do Na2Cr2O7, H2SO4, and water first. If I do that right now my answer is this. This turned into carboxylic acid. And then I can do my BH3Cl. So BH or BHCl2 thing. THF, H2O2, NaOH, and water. So now if I do that, this is just going to turn into that. So it was a little tricky. You can't do the Na2Cr2O7 first. Okay, next one is a synthesis question. Well, looking at the final product here, the only way you know how to make thiols is a substitution reaction. So when you look at this, you have to think, well, I got to this because before it looked like this. And I did an SN2, and that SN2 was NaSH with DMSO or something. So then you're like, okay, let's go back to the beginning maybe. If you go back to the beginning, the only thing you can do on alkanes is Br2 light. If you do Br2 light, you get this. So I just have to move this Br to that spot. Well, to do that, you can just do elimination. So I want to do elimination like this. Br2 light. That elimination was anti-Zeit-Steph, so we're going to go tert butoxide like this. And then you make this go to that, which is Br added to less substituted side, which is HBr ROOR. So that would be your answer. 4 steps. Next question, you went from 4 carbons to 5 carbons. The only way you do that is with CN. So we have to keep that in mind. I know right before this, it needed to look like this. So then you ask yourself, well, how do I get a CN? Oh, at this step you did H2PT. Well, then you ask yourself, how do you get CN? You get CN if this was like a bromine before. So I just have to make this go to that now. Now you can do this multiple ways, but I think one of the easiest ways would have been to first take this and make it a double bond, and then double bond can put a Br at the end. So this is NBS HB, or NBS over CH2Cl2. The first part was like 2Na over NH3, and then this can go to this with like H2PT. Now, I did say it was 4 steps long, so if you wanted the fastest way, what you could have done was you could have just kept this double bond, right? So you could have just kept this double bond from here. You could have done substitution right now, so you can do NaCN, DMSO here. You would keep this double bond, and when you reduce with H2PT, it would reduce both the double bond and the CN. So that way it would be 1, 2, 3, 4 steps. If you reduced first, it's okay. You would just get the answer in 5 steps. Okay, the last page is just a little extra stuff I added regarding chapter 10 stuff. So let's take a look at it. The first part is a Diels-Aldrich question. You have to remember, whenever you start with the cyclic compound, you make a bicyclo. So we're going to do that. You make your little bicyclo. So the middle part will look like this. The double bond goes here. Since you can't do the partial positive and negative here, it doesn't matter here either. But you do have to know which one you listen to here, and that one is carboxylic acid, so we're going to make that one go dashed. And the other one is trans to it, so that one goes wedged. Next question is like Claisen. No, this one is cope. You can see that the double bonds are 1 and 5 spot. So to like work with that, just make this little structure. Just go in 1 and 5 like this. So make a double bond here, make a double bond here. Go 1, 2, 3, 4, 5. Okay, you can see on 5 I also have this methyl. On 4 I have this methyl. On 3 I have a methyl and a ethyl. Like this. And that's it. So at this point, you just erase and go. So make your little arrows first. The arrows can go either way. So let's say we go this way. Then they would look like that. And then I'm just going to erase and go. So I go erase this. And this forms a bond here. Erase this. Forms a bond here. And then erase this. And that forms a bond here. And that would be your answer. Keep it simple. Next one is what is this, Claisen. Again, I would do it in that little format. So call this 1, call this 2, this is the 3, 4, and then 5. So that's your little structure. 1, 2, 3, 4, 5. On 4 I have a methyl, on 5 I have a methyl, like that. Let's erase the numbers. And then we make a little arrow, so let's go up. This goes here, this goes here. Okay, we're gonna erase and go, so we go erase this and erase this double bond, and it forms a bond here. Erase this bond, that goes right there. Last one is erase these two to form your ketone, like that, and that would be our answer. Not so bad. Alright, next one is just mini reactions. So here the reagents were just this is just acid catalyzed H2SO4 but with ethanol. So you add the H here and then the O ethanol goes in the middle, and that's that. I just drew it weird so you guys get confused, but this is just acid catalyzed. The next one is adding a O methyl at the end. Well, that one is add a H here and add the O methyl at the end. And that one is hydroboration, so we do BH3, THF. Step 2 is Na, or H2O2, NaOH, and then instead of water I use methanol, CH3OH. Alright, next one is HCl. So this is where you have to figure out which double bond is better, and this is clearly in thermal conditions. So out of the two double bonds, if I put the H here, I get a secondary allylic. If I put the H on the other side, I get a tertiary allylic. So we're going to go with the tertiary allylic. So I know my first intermediate looks like this. Positive and double bond. They want the thermal answer, so I know I'm going to put this here, form this answer, positive there, and then the Cl can go there. So your answer should be that. That's the thermal answer. Kinetic answer would have been if you just put it there. Next one is another Diels-Alders. Here we do have to figure out the partial positive and negative. So let's figure out who we were listening to. Well, I'm listening to this guy, the NO2, and here we're listening to that. The O-methyl is the best donating group. You make a partial negative on top, partial positive on bottom. Let me redraw this. So you got a NO2, you have a methyl, and then the methyl is on the same side like that. So NO2 pulls, so you get a partial positive here and a partial negative here. You can see that they're not matching up right now, so let's draw the NO2 on the bottom. Now you get the partial positive on top, partial negative on the bottom. Okay. If I redraw this part, we have this O-methyl and this partial negative, partial positive. Everything's matching up. So first we make our little cyclohexane thingy. Okay, first thing, the OCH3 is pointing in, so it has to go wedged. This is on a sp2, so it doesn't matter. And then NO2 was the one I listened to, so that one goes dashed. The methyl is trans to it, so that one goes wedged, and this methyl also goes wedged. So that's the answer. Okay, and that puts an end to our test. Yay! Okay, some of that stuff we definitely didn't know. I think near the ending, we definitely need to know all of that stuff, including this naming and stuff. Some of this top part got a little weird. This wording was a little bit weird. You don't completely know how to do the strain question, so don't worry about it. Isomer question wasn't on your first test, so I don't know. The multiple choice were totally legit though. Okay, well, good luck on your exams. I will see you guys during the mock exam. If you're seeing this video after the mock exam, then good luck on your test. And if you're seeing this after the test, then why are you looking at this video after the test? Go chill. Alright, take care guys.